we are now ready to discuss a context-sensitive pointer analysis, which is a mid-path between a context-insensitive pointer analysis and a region-based analysis. So consider this this function bar, and let's say it could be called in two different contexts. And recall that we can choose how we want to define context. For example, we could define context based on the call site of bar. So here that would mean that maybe there are just two call sites of bar, and there could be multiple call sites of the function that calls bar, but we are not going to consider them as separate contexts. So that would mean that it's a depth one call context. Irrespective, let's just say that there were two contexts in which bar could be called, and I'm going to, for the rest of the discussion, assume that I'm using depth one call context for my context. So let's say there's a function foo that's being called at location f1. So foo can be called in context f1. And there's another location f2 where foo can also be called with a different set of arguments and a different set of return values. So foo is this function which takes an argument. The formal argument name is z, and it has some body. So when we do a pointer analysis, a context-sensitive pointer analysis, firstly it's an inter-procedural data flow analysis, and we analyze each function in the context that it occurs in. So for example, bar is analyzed in context b1 and b2, as we said, and foo is analyzed in context f1 and f2. Now notice that actually there are, if I look at depth 2 call context, then there are 4 different combinations in which you could you could kind of analyze foo. For example, b1 f1, b1 f2, b2 f1, b2 f2. But we're going to restrict our call context, and assuming that there are depth 1 call context, then there are 2 call contexts for bar, or 2 contexts for bar more generally, and 2 contexts for foo, f1 and f2. Okay, so let's move on. Now each variable, whether it's an argument, a local variable, return value, is analyzed in both call contexts. So that means that, let's say there's an argument z in foo, then z has 2 different, it will be analyzed in 2 different contexts. So zf1 will be when z occurs in context f1, and zf2 will be when z occurs in context f2. For example, we will have different points to relationships for zf1 and zf2. For example, zf1 may point to some variable x or y, whereas zf2 may point to some other variables a or b, and these sets could be potentially intersecting. Similarly, x could be, x could occur in 2 different contexts, xb1 and xb2, because x is a variable that's occurring in bar, so we look at bar's context when we version the variables. Similarly, y is yb1, yb2, because once again it's occurring in bar. M and n are also variables, and those are also going to be versioned using the context. So mb1, mb2, nb1, nb2, and they become completely different quantities that get analyzed in their respective contexts and while doing the inter-procedural DFA. Okay, so let's get a sense of how these different quantities behave. So for example, when z is called from f1, then what we look at, the quantity that we consider is zf1. That's what the versioning means. But if z is called from f2, then we look at zf2. And from that we can say that when we analyze, when we do the data flow analysis, then when we do this dispatch from this statement f1 to the function foo, then whatever is the value that's being analyzed for x at that time, so let's say the points to set of x, then that gets copied to whatever is the value of z in the context in which it is called, which is f1. That means zf1 is updated using xb1. If I was analyzing bar in context b1, then when I hit this statement and transfer across this function call, then the value that I'm actually tracking for x is xb1, because I'm analyzing bar in b1. And then when I do the transfer, then I analyze foo in f1. So zf1 becomes is updated using xb1. And in the case of a points to graph, recall the updation basically involves addition of outgoing edges. So in other words, the outgoing edges of zf1 in the points to graph will be a superset of the outgoing edges of xb1. Now, similarly, when I am here, then let's say I'm again analyzing bar in context B1, then ZF2 this time, because this is being called, this time I'm analyzing it in context F2 because that's how I reached foo. So ZF2 will be updated using YB1 because Y was being analyzed in B1. Now the same thing will happen for B2. So for, let's say the same bar will be analyzed in B2. So then I'm going to be tracking XB2. And now I'll update ZF1 using XB2. And similarly, I will update ZF2 using YB2. And so I get these kind of set of constraints that the outgoing edges of ZF1 should be a superset of the outgoing edges of XB1 and so on. And effectively, this means that ZF1 should be a superset of XB1 union XB2, because I mean, if I take these two constraints in conjunction, then that's equivalent to saying that ZF1's outgoing edges are a superset of XB1 union XB2. Now this is where there is a precision loss, because I am combining the XB1 could be pointing to, let's say, some set of objects, and XB2 may be pointing to some different set of objects, overlapping or not overlapping, doesn't matter. And when I look at Z, then I union both of them, and that's a loss of precision. For example, in contrast, if I was using a region-based analysis, then I would have tracked these separately. For example, I would say XB1, then execute the transfer function of foo on XB1 as though it's completely executing in isolation, and that would have been transferred the value to M, whatever it is. So I would have treated foo as completely different functions in context B1 and B2, and they would have just been as though the whole function foo is inline separately for B1 and B2. But when I do a context sensitive pointer analysis, not a region based analysis, then I am doing this approximation where I am taking the union, because ZF1 is updated both using XB1 and XB2. Similarly, ZF2 is updated using both YB1 and YB2. So this is a precision loss over region based analysis, but this is a precision improvement over context insensitive analysis, because now ZF1 and ZF2 can be pointing to different objects, because in a context insensitive analysis, I would have had just one Z, which would have been the union of all these four, XB1, XB2, YB1, YB2. Or in fact, let's say if B1 and B2 were not in context, then all arguments that appear at foo as an argument to foo, actual argument to foo, will appear, will all of them, whatever their points to set are, will update the points to set of Z, and there will be interference across call sites because of that. So this is a precision improvement over context insensitive analysis, because I'm tracking ZF1 differently from ZF2, but it's a precision loss over region-based analysis, because I am actually merging XB1 and XB2 to obtain ZF1, whereas a region-based analysis would have tracked even XB1 and XB2 separately. Okay, so all right, so let's take some examples of statements that can occur in the body of foo. So one of the statements that could occur in the body of foo is an allocation statement. So let's say at location L inside foo, I'm allocating a new object using this statement P equals new something, some type. Now in an interprocedural DFA with context sensitivity, we would say that L, the location L, is occurred in what context of my analysis? Did L occur in context F1 when I came to F through this F1 call site, or did L occur when I was analyzing it through F2 call site? And so I will track L F1 and LF2 as separate abstract objects in my analysis. And so that is also a source of precision improvement. So for example, I would say PF1, which is P occurring in F1, the points to set of PF1 would contain LF1, and the points to set of PF2 would contain the location LF2. We're going to see later how this improves the precision. Recall that in a context insensitive analysis, I would have just said that the points to set of P includes L. But here I'm kind of making a more fine-grained statement. I'm saying if P occurs in F1, then it contains LF1. If P occurs in F2, then it contains LF2. But we notice that I'm not drawing any diagonal relationships between these three. Okay, Now let's say there were other statements like assignment, copy, or dereference, and I'm going to use my standard points to assign analysis rules. For example, if I'm analyzing the procedure in F1's context, then I'm going to say AF1 should be updated using star ZF1. I'm abusing notation a little bit. Star ZF1 basically means look at all the outgoing edges of ZF1 and then look at their outgoing edges, and all of them should be a part of the outgoing edges of AF1. And so on, right? So for example, this D equals Z basically updates DF1 using ZF1 and so on. And if I analyze the same body in a different context, say F2, then I update draw constraints of the corresponding variables. For example, here I'm going to say AF2 is updated using star ZF2, DF2 is updated using ZF2, and so on. So this is also a precision improvement, because let us say that Z was different, Z had a different points to set because of F2, then I'm going to have different values that are going to flow into AF2 than what will flow into AF1. And so this will give me more fine-grained, more precise information than a context-insensitive analysis. Now, let us say that foo eventually has a return statement, and let's say it's returning a value, and let's say it's returning some variable E. Then, depending on what context I was analyzing foo in, I would have two different values for two different points to set for E, so EF1 and EF2. And then when this return value goes back, then it goes back to the call site where there must be a variable which is being assigned to the return value. So in this case, let's say at F1 it is M, and at F2 it is N. So when I update, then if I was analyzing foo in context F1 and then this happened, the return happens, then we update M using EF1. And similarly, I update N using EF2. But I don't update, for example, M using EF2. Right? So this is the precision improvement. Mathematically, this can be said as that MB1 should be updated using EF1. So if I'm analyzing bar in B1, then MB1 should be updated using EF1. If I was analyzing bar in B2, then MB2 should be updated using EF1 as well. So these two represent the cases where the call happens through this F1 call site. And then NB1 should be updated using EF2. So because N is occurring at F2. And NB2 should also be updated using EF2. And because the updations are addition of edges, so in constraint form, you can say NB2, the set of outgoing edges in the points to graph from NB2 should be a superset of the set of outgoing edges from EF2. So once again, this is a precision improvement over context insensitive analysis, because when I go back, when I do the return, function return, and I go back to the caller, then I can track more precisely what values should flow into the return value. So for example, M would only get influenced by EF1 but not EF2, and so you would avoid paths where, let's say, foo on Y could have returned some very large points to set, and foo of X was going to return a very small points to set in its return value. Then M would still have a small points to set and N would have a large points to set. Whereas if I was doing a context insensitive analysis, both M and N would have had a large points to set. So in a context insensitive analysis, I would have said that M is a superset of E and N is a superset of E. And those were the only two equations. But now I have 4 different quantities and 4 different constraints which are tracking this more precisely. Okay. Now let's take an example. So let's say one of the statements in the body of foo was L:E equals new. So this is an allocation statement, and then you return E. So if you return E, then recall that E is basically holding L, one of the points to sets, one of the points to elements or abstract objects that E can point to is L, and depending on which context it is, it will be either LF1 or LF2, and so that value will flow into the returned value. So if I was analyzing foo in context F1, then the value that gets returned is going to be pointing to LF1, and that's what's going to flow into M. So M would be updated using LF1, because we're tracking this precisely and saying that LF1 is what gets allocated when I get called through F1, and then that's what gets returned to M. Whereas if I get called through F2, then I allocate the abstract object is called LF2, and that's what gets returned into N. In other words, MB1 for context B1 in bar is updated using LF1. Similarly, MB2 is also updated using LF1, and NB1 and NB2 are updated using LF2. Are both updated using LF2. Notice that this means that MB2 may or may not, it's possible for MB2 to not alias with NB2 if LF1 and LF2 are different allocations or abstract objects, which they are in this example, which basically means that I can kind of assert here that M does not alias with, or star M does not alias with star N. Now this assertion was not statically possible to ensure with the context insensitive analysis, because in a context insensitive analysis we would have said, hey, they can both point to allocation site L objects. But in a context sensitive analysis we are saying M can point to allocation site L in F1, but or abstract object LF1 called LF1, and N can point to abstract object called LF2. They are separate abstract objects and disjoint in the objects that they represent, and that's why they the accesses through those two pointers cannot alias. This is how the precision improvement happens. Now I'm going to switch gears and make this more formal. So first of all, I'm going to define some notation. So let's say bar, in our example, bar was being analyzed in two different contexts, B1 and B2, and similarly foo was being analyzed in two different contexts, F1 and F2. Then I'm going to use this notation saying B1 turnstile operator body of bar, which basically means that body of bar is analyzed in context B1. Body of bar is also analyzed in context B2. So B1 turnstile body bar basically represents that if we are analyzing if body bar is being analyzed in B1, that's what this means, or this represents the predicate that body bar is being analyzed in B1. This represents the predicate that body bar is being analyzed in B2. Similarly, body foo is being analyzed in context F1, and body foo is being analyzed in context F2. In general, if I write C, this turnstile operator E, I'm saying E is being evaluated or analyzed in context C. Okay. So using this, I'm going to formalize and give you some inference rules that basically complete this context sensitive pointer analysis. So if a statement, an allocation statement of this form, P equals new something something at allocation site L, is being analyzed in context C, then this abstract object represented by this allocation site, which I'm going to call LC in context C, so I'm going to call it LC, must belong to the points to set of PC. And I'm going to use this notation. Earlier I was not being very precise in the notation, but now I'm going to be more precise. So I'm going to use the square brackets notation. So square brackets of A represents the outgoing edges of A in the points to graph. So here this basically means that LC would belong to the outgoing edges of PC. So PC would be pointing to the abstract object LC. And notice that both P and L have been versioned using the current context C. And this is what we saw using our examples as well. So once again, if this allocation statement is being analyzed in context C, then PC's outgoing edge includes LC. All right. Similarly, we can generalize for other points to rules, the Anderson's standard Anderson's analysis that we previously discussed for an intra-procedural case. So let's say we have a copy statement P colon equals Q being executed in context C. Then we update the outgoing edges of PC using the outgoing edges of QC. Now notice that I'm using the subscript C in both sides. So for example, if there was another context D in which this was happening, then nothing gets changed or read from the value QD and PD. So this is only, so whatever is being held or whatever QC can point to, now PC can also point to, and that's what this update, this conclusion of this inference rule indicates. Similarly, let's look at a dereference. So P colon equals star Q. then I look at all the points to set of Q in context C, that is, let's say QC, and square brackets around that. If there's an abstract object R that belongs to this outgoing edges of QC, then we update the outgoing edges of PC using the outgoing edges of R. So, I mean, this is standard, we have already seen this. So if QC could point to R, that's what this means, and R could point to some other object C, S, then PC should also point to S. That's what the conclusion says, that whatever are the outgoing edges of R should be added to the outgoing edges of PC. Alright, that's dereference. And finally, assignment. So it's very similar. Whatever are the so star P colon equals Q being executed or being analyzed in context C. So look at all the outgoing edges of P. Let us say R belongs to the outgoing edges of P, PC, P in C, context C. And then you update the outgoing edges of R, because this is an assignment. You update the outgoing edges of R using the outgoing edges of Q in context C, or the outgoing edges of QC. Okay, so the last four rules that we saw are pretty standard. They are the standard Anderson's algorithm, just that this time I also introduced a context C. But there are two rules related to function called dispatch and return, which are special, kind of specific to the context-sensitive analysis. So let's say I am analyzing a function call t colon equals fx occurring at location L, and this whole statement is being analyzed in context C. For example, if this could be, if this was a bar function, then L would be f1, f would be foo, and C would be one of the contexts in which bar is being analyzed, b1. And let's say the body of f is E and the formal argument of f is A. So recall it was Z in our foo example. Then basically I was analyzing this X in context C. So whatever is the points to set of X in context C, I need to copy that to the points to set of A in context L. In other words, I need to update the points to set of AL using the points to set of XC, because that's what's going to happen in this transfer from the caller to the callee. The caller was executing in context C. The callee will start executing in context L, because I'm assuming a one depth call context. So and then I have to simulate the calling, the dispatch. In the dispatch, it basically copies the actual arguments to the formal argument. So I use the copy rule and just say that update AL using XC. In other words, the outgoing edges of AL should be a superset of the outgoing edges of XC. Moreover, we add another conclusion. So there are two conclusions because of a function call. The second conclusion is that the body of F can be analyzed in context L. And this is, and that would be used in by this fact. This property can now be used while we are analyzing the body of F. Okay, similarly, when I return, so let's say there was a function call and inside L, there was a return statement. So I would analyze the return B inside the body of F, which is E, in context L, because that's where, let's say that's how I was. So if this function called dispatch occurred in context C, this was the body of the program, of the function F in the program, and inside this program there was a return statement that was kind of analyzed in context L, which means the dispatch actually happened here. Then whatever is the value that's being held in B should get copied to the returned value T. The value that's being held in B is being tracked using the corresponding version BL, and that should get that should be used to update the value T in context C. In other words, TC should be updated using BL. So BL is the callee value, TC is the caller's value. The outgoing edges of TC should be a superset of the outgoing edges of BL. So this is the return rule. Finally, we can combine context sensitivity and field sensitivity. It's nothing, it's nothing out of the ordinary. But I'm just going to use some examples I'm just going to show some rules to kind of concretize this. So first of all, I'm going to use a notation where it says outgoing edges of A subscript field represents the outgoing edges of A labeled with field FLD. Recall that when we do a field sensitive analysis, we label the outgoing edges saying that I can point to this object using this field, right? So if I analyze P colon equals Q pointer dot field in context C, then this is equivalent to saying, for example, star Q, except so we do, the first thing we do is we look at all the outgoing edges of Q. So that's, let's say R belongs to the outgoing edges of QC. So Q in context C, so R belongs to the outgoing edges of QC. Then we update using the outgoing edges of R. So this is as good as a dereference. So we update using the outgoing edges of R, but with the caveat that I only update using those outgoing edges of R which are labeled with field. So that's what this notation means. So I update the outgoing edges of PC using the outgoing edges labeled with field of R. So in other words, in the constraint form, the outgoing edges of PC should be a superset of the outgoing edges labeled with field of R. And finally, actually the labels that I have written here are kind of mismatched. This should have been called deref, and this is assign. These are the names we've been using all through. And here, this is basically similar. I'm just going to use the assign rule, just that I'm going to use a field subscript for the outgoing edges once again. So if I have p.fld colon equals q, this is similar to saying star p colon equals q, except that is in a field sensitive way. I need to do it. So I look at all the outgoing edges of PC, because this is a dereference, I do a star P, so I look at all the outgoing edges of PC. Let's say R is one of those outgoing, pointees, or the destination of the outgoing edge. Then I update its outgoing edge, the R's outgoing edges using Q. But I don't, and all the new edges that I add because of this assignment will be labeled with FLD. If they already existed, then I just add this label to those edges. That's pretty much it. And so that basically means that the outgoing edges of QC are used to update the outgoing edges of R, but only those outgoing edges of R which are all the new edges are annotated FLD, and if those edges already existed, then the FLD label is added to those edges if that label already didn't exist. Said differently, I just add all the new edges that I add to my outgoing edges of R should have the label FLD. So this is how you could combine context sensitivity and field sensitivity. Recall that field sensitivity requires you to have certain amount of type safety. You cannot do pointer arithmetic or unrestricted fields. But when you can do field sensitive analysis, it's a very useful way of improving precision.